Let us move on to the next problem, which is a problem on dam. This will be problem number 3 for us, and it tells that water stands at a height h behind a vertical dam of width w. Locate the center of pressure on the dam. First of all, definition of center of pressure is defined to be the point at which the line of action of resultant force of pressure intersects the dam. So we shall approach the problem like this. We shall find the resultant force of pressure acting on the dam, then resultant torque acting on the dam taken about a suitable point at the base. From the two results, we shall determine the line of action of resultant force, and hence you can find from there the point at which this line intersects the dam, and that is the center of pressure on the dam. So let me complete my figure. Here is a water body standing on the left hand side of this dam. Right hand side there is only air, and they have told us the height of the water body, that is h, and the width of the dam is small w. So you understand, water standing on the left exerts a pressure on the dam to the right, a pressure that is a sum of atmospheric pressure and hydrostatic pressure. On the other hand, the air on the right of the dam exerts atmospheric pressure towards the left onto the dam. So therefore, when you go for the net force acting on the dam, this atmospheric pressure term will drop out from the calculation. We shall see that in due course. Now, what are the effects of the horizontal forces of pressure acting on the dam? There are two effects. The resultant force tends to push the dam along the base, and the resultant torque of the forces of pressure that tends to rotate this dam about the base point O in the clockwise sense. If I could draw a horizontal axis to this point O, the resultant torque will tend to rotate the dam in the clockwise sense about this axis shown in my figure. So first of all, let us find the resultant force acting on the dam. There are two methods. In the shortcut approach, we can find out the average force acting on the dam. That is the arithmetic mean of the pressure at the top and the pressure at the bottom. And then you multiply that by the area of contact between the dam and the water. Another method is integration, and we shall go for the second method, because in any case, to get the resultant torque about O, we have to take help of integration method. So let us make the figure slightly smaller and squeeze out some space to start writing. So in the method of integration, as usual, we consider infinitesimal strip of the dam that you can see here by this red shading. This one has got a width equal to W, the dam's width only, and its position is at a variable depth small h below the free surface of water. So here you can see in my figure, this length is h, and the height of this red strip, that is an infinitesimal value, that is dy, and also the height of this strip only from the bottom, from the base of this dam, that is taken to be y. And since this dy is a very small amount, we can say that capital H, the whole height of this water body, that can be written to be the sum of small h and y. Both small h and y are variable quantities, because I can take this infinitesimal strip of dam anywhere along its height. It follows therefore, small h is given by the height of water minus the height of the strip as measured from the bottom of this dam. Now, what is the area of this infinitesimal horizontal strip of the dam? This is taken to be dA, and this dA is equal to the width W into its height, that is dy. So dA is also a very small amount, and you can understand here the pressure of water is acting to the right onto this strip, and the pressure of atmosphere is acting to the left on this strip, and therefore the net pressure acting on this strip is given by pressure of water, that is atmospheric pressure plus hydrostatic pressure H into rho into G. Here let me tell you, density of water is taken to be rho, and h is of course the variable depth of the strip in question from the free surface of water. So h Pa plus h rho g, that is the pressure of water acting to the right minus pressure of atmosphere acting to the left given by the air only. And you can see here the Pa terms cancel out, leaving us with the net pressure to be equal to the hydrostatic pressure, that is h into rho into g. But since we have taken the small h to be capital H minus y, we might express that the net pressure acting on this horizontal strip shown in red color, that is given by capital H minus y into rho into g. Once we get the net pressure, let us find out the infinitesimal force of pressure acting on this element, and that force we'll be calling it dF, because the area involved is very small, that is dA only, that is given by P into dA. Put the value of P, that is H minus y into rho into g, and the value of dA that was found to be W into dy, W being the width of the dam and dy being the height of this infinitesimal element being investigated.
Hello students, you got a glimpse of our video lessons through this small lecture. We have hundreds of lectures like this one covering various topics of advanced school level and intermediate physics in our website. They are exhaustive and often accompanied by elaborate diagrams to make concepts even clearer. They are taught with passion and sometimes with a bit of fun. So, at the end of the lesson, you have a commanding grip on the subject and you are ready for the board and competitive exams. Subscribe at physicsacademyonline.com to access video lectures of highest standard on various topics of physics.